Okay, good morning, everyone. So this is the 5th day of the school, and I hope that still you are able to concentrate. Okay, anyhow, so today's first talk will be by Professor Tanja Mehlstäubler from PTB in Germany, and she will have 2 lectures. Today is one, and the other one is on Monday, right? Tuesday, okay. And she is going to talk about optical clocks and probably applications also, something like that. Tanja.
Okay, yeah, thank you very much, Subhadeep, and thanks for the invitation. I just arrived yesterday, and yeah, I must say it's a pleasure to be here. It's the first time in India for me, so I don't know so many things yet about India. I'm very excited to discover. And I take the opportunity today to teach you a little bit about optical atomic clocks. I saw in a program that you have been already well prepared. There was a lecture by Subhadeep about atomic clocks in general, microwave clocks. Then you had 3 lectures by Fritz Riele, my colleague from PTB, on accuracies, systematics, how to evaluate measurements, the SI standards. So many things I don't have to repeat. Then I think there are also lectures on ion traps, dedicated ion trapping lectures, then lectures by Anders Kasberg on laser cooling. So basically the whole potpourri, the foundation is already laid, and I don't have to go into the details, otherwise it would also blow the talk. So I will really focus now here, what is the specific thing about a clock? Yeah. Of course, we need all the ingredients. We need the ion traps, we need the laser cooling, we need the quantum metrology. But since there have been so many lectures, I will focus here in this lecture now, really what makes the clock, and hope to pick some issues that have not been lectured here yet, like frequency combs, frequency transfer, and very technical things that are needed and are the basis for an optical clock. So as Subhadeep said, I'm from PTB, that's the German National Metrology Institute. Actually the oldest one in the world. I don't know if Fritz said that. It was founded in 1887 or so, long time ago. It is the very first one by Siemens and Helmholtz. And at the same time also a professor at Hanover University, which is close to Braunschweig, where I'm teaching. And this is how our team looks like. So at the moment, we've been growing a lot in the past years. So we are 28 people. One of you is also here, Suyash. I don't know if he's in the audience. Hi. So he was visiting for 3 months and working with us in Braunschweig. And yeah, I'm also guest professor at Osaka University in Japan. That's why we do have a very vivid exchange with Osaka and also with Tokyo at the NICT, where they're also building optical clocks. So our master, PhD students and also postdocs are exchanging at this level between Japan and Germany. And yeah, of course, you're welcome to visit. So look for us at the quantum metrology webpage under quantum clocks and complex systems, and you will find us, and let me know if you want to visit like Suyash did. It's always a pleasure to exchange also with India, of course. Yeah, so this is just a short overview how our group looks like. Since we're rather large, we are subdivided by 5 teams, 5 dedicated topics. I will mainly focus here on the first 2 ones in these 2 lectures. So this is also how it started out. We proposed the concept of a multi-ion clock in 2012, and you will hear about this also during this optical clock lecture. So how can we scale up the qubits, the ions for quantum metrology? Then we're doing precision spectroscopy with the terbium ions. There we're testing fundamental physics, searching for deviations of the predictions of Einstein's general relativity, searching for dark matter, doing isotope shift measurements. A lot of this will be part of the lecture of next week. So the applications of optical clocks. So on Tuesday, I will focus on this topic more. And the other 3 topics I will not dive into, because this is yet another thing, like we're also researching on the dynamics of Coulomb crystals. We've been the first group in the world actually who saw and created topological defects in a very controlled way by symmetry breaking phase transitions. And then I had to learn a lot about solid state physics again, go back to the old textbooks, learning about the Frenkel-Konterover model, about how do defects, king solitons propagate in such nonlinear media, energy transport, nanofriction. We studied really how do atoms, atom by atom, slide in such a microcrystal. So that's super interesting physics, but of course it's not quantum metrology. That's why I will leave it out of this talk. But if you're interested, look for our papers here. And then we have also very technical projects, industry projects. We're collaborating very closely with German and also European industry, big companies like Infineon, who are CMOS chip manufacturers. And we're building ion traps for quantum computers, for quantum metrology, benchmarking them and making this technology transfer to industry. Okay, but in this lecture today, I will start really on the clock aspect. So this is now the outline of the talk. After a short intro, I will give you an overview of what are the ingredients needed for an optical clock, what type of optical clocks exist, very in general. I will keep everything very conceptual. So the idea is that you get an overview. Then what is needed for clock comparisons in fiber networks, and in the end give you examples of concrete recent clock comparison campaigns with a focus, of course, of Europe, where PTB was involved. So I should say this is, of course, a bit biased, the talk, because I will focus here a little bit on the European clock comparisons. But needless to say, rather similar things are going on in all continents. So Asia, Japan, China, also India is building clocks now, and you see optical clocks all over the world popping up, and of course also strong the Americas. But there's for sure a bias in the talk on Europe. Okay, so I think this slide you must have seen many times, hopefully. This is the development of microwave clocks over the past, almost getting close to centuries, so since the 1950s. The constant improvement on microwave clocks, as you have seen in Subhadeep's talk. Now today, we will talk about optical frequency standards. And they look as if they have a much steeper slope, and I've been crossing now the microwave standards. And what is really very important for the optical frequency standard, I think what really triggered this race in speed and in improvement was the invention of laser cooling and trapping of atoms. So in the 1980s to 90s, eventually leading to the Nobel Prize in 1997, this high level of control of single atomic systems, of single quantum systems, dramatically enabled us to go for this ambitious optical domain where everything is more sensitive in terms of the phase. You can imagine a laser with a very short wavelength, a few hundred nanometers, compared to the microwave, where we're speaking of meters of wavelength. It makes everything much more challenging, because if you're moving, the phase error you get is dramatic, if you have a very tiny wavelength. But since we are able now to cool the atoms, to trap and locate them, and bring them to the ultra-cool temperature of microkelvin, this really enabled the optical frequency standard, and with a dramatic improvement. And today, I should say, they're holding the world record in any measurement that you can do, in any physical quantity that you can measure. We're just breaking the 10 to minus 19 record now. So most of the clocks are at the 10 to the 18 level now. So time and frequency is the physical unit that you can measure with orders of magnitude better than anything else. It's rather remarkable. So this is just a teaser to make you curious how we do that. And this is now a zoom up that should tell you, I guess, well, the slope is steep, but there's also really hard to cross this 10 to minus 18. If you look into the detail, it's not that we're just doing whoop and everybody is there. No, people are struggling now for more than 7 years. And then more and more clocks are piling up at this low 10 to minus 18 level. But to really make this another order of magnitude is a big challenge. And this is where many people are competing in this race of the world record of the best clocks. And now coming back, why are optical clocks so much better and more accurate and precise than microwave clocks? Well, the first very conceptual argument is that you're using basically a finer scale. As I said, instead of using a microwave with a wavelength of several meters, you're using now an optical wave with a wavelength of hundreds of nanometers. So this is of course exaggerated, but if you go from inch to centimeters, that already gives you a finer scale. Sorry for that. And but of course you can now imagine if you improve this by 10 to the 5 and 5 orders of magnitude, you just get with one measurement much more information, much more resolution. That's why you can go to shorter averaging times. And the other aspect is that you have smaller relative uncertainties. So be careful. In a way, it's a little bit cheating because we're always talking about relative uncertainties. So we divide by the frequency. So of course, if I crank up my frequency, given the same delta nu, I immediately win orders of magnitudes. And let's have a look at the systematics that clocks have. So I think this has been extensively discussed by Fritz Riele. So, but let's just look at the systematic uncertainty UB. So what are the typical shifts in atomic clocks? You have field shifts like the Seemann shift, the AC Stark shift. You have relativistic shifts, time dilation, first and second order, collisional shifts from the background gas, giving you a phase shift, and technical shifts like the AOM, phase chirps, index of refraction that is changing. And can you imagine which one of these shifts are just constant in scale? So basically, if you have a shift which is independent on the frequency that you're using, does anybody have an idea which one of these shifts would fall under this category, independent of the frequency that you're using? 1, 2, 3, or 4? I'm open for suggestions. Which one of these shifts does not care if you're a microwave clock or an optical clock? The second one, time dilation. So you're thinking of the Doppler shift, for instance, which is the velocity divided by the wavelength. Be careful, it's relative. It's relativity, and it's unfortunately a relative shift. But, well, we have what else? Well, I highlight them here. So the field shifts, for instance, the Seemann shift, the AC Stark shift, gives you a constant offset, yeah, because it doesn't matter which transition you interrogate. The levels, the atomic levels are interacting with the outer world and are shifted in frequency. And this is now, let's say, a few millihertz, very tiny shifts in terms of Seemann and black body radiation shifts, or the collisional shifts when the background gas creates molecules and shifts the energy. Always when you have a shift in the atomic energy level, then this is an absolute shift, and it doesn't matter really what transition then you're probing. And then you win dramatically, yeah, because then when we divide with the frequency divided by nu, you see a microwave clock here would end up to be in the 10 to minus 14 region. But if I'm working in the optical domain, I immediately put in a 10 to minus 19 region. And this is this dramatic improvement when I'm going from microwave to optical, because many of the shifts that gave us a big headache in the microwave region, the collisional shifts and the field shifts, they're just blown away by orders of magnitude. And it's not really cheating, because I will show you in the end, and also next week when we're talking about applications, that most of the time when we're doing physics measurements, or when we're searching for new physics or for navigation, actually it's the relative stability and the relative accuracy that matters. So it's really a significant improvement to go from microwave to the optical domain. But in fact, the technical shifts and also the relativistic shifts, they are giving us the same headache. And optical clocks are at the moment limited by time dilation, by the motion of the atoms, because this scales relative also with the frequency. The phase shift is very critical. Okay, but then on the other side, you have the statistical uncertainty, UA. This is also what Fritz already told you this week. This is just a warm-up and a reminder. For sure, you have seen that slide to remind you that you have the choice of building a stable and accurate clock where you always hit the target very nicely and have very low noise, Or you just have an accurate clock, but with a lot of scatter. So that means it's rather unstable, but the mean is correct, it's accurate. Then we have this, what we call in our language reproducible, because it's unfortunately has an offset, but it's very stable. So you always obtain the same measurement. This is actually a very dangerous clock. Many of us have such kind of clocks because you think you have a wonderful clock and you evaluate it to be at the 10 to minus 18 level. But if you don't know about this magic offset, maybe you're wrong. But does anybody have an idea why these reproducible clocks are nevertheless very interesting? Even though they're wrong, but what could be very, yeah? A very stable time reference, yeah, that's very good for instance, navigation, yeah? Because if I'm navigating, I don't care about an absolute value. I just want to see differences with GPS. Very nice. Any other idea? Any other suggestion? To use it for what? Yes, yes, exactly. Yeah. So I think I am getting what you mean. So if you just have an offset, you can correct for it and use it for a clock. But even if I don't know the offset, even if I'm completely blind, maybe there's an atomic constant that I don't know, a polarizability, a G factor of my magnetic states, something that ab initio calculations can't calculate very well, and I can't deduce it. But at least I know it's an atomic constant, so it doesn't change. So I don't know really, I couldn't put the number to the offset, but I know it's constant. So, well, I give you a glimpse. That will be actually Tuesday's lecture, where we talk about the search for new physics and the application as atomic sensors. Because if I use such a clock and I want to measure something, for instance, relativistic geodesy, I want to use clocks to measure height differences on a mountain, on a valley. I always do relative measurements from A to B, from B to C. These are relative measurements. And then if I know that my offset is constant, I don't care because I'm only doing relative measurements. So it's a very good quantum sensor. Or if you're looking for new physics, you're testing Einstein's general relativity, you're searching for dark matter, and you don't care if you don't know maybe the polarizability of the atom or a G factor. But you're looking again differentially for changes while your clock is orbiting around the sun or rotating in the universe, or you're comparing different clocks. So you don't know about such a blind offset, which is only due to a constant. And that's why these reproducible clocks are for many applications as good as the stable and accurate clock, I would claim. And this will be a lot in a Tuesday lecture. Okay, yeah, thanks for the contributions, and I appreciate that you're courageous to discuss. That's very good. Now, let's go on. So this is just to show you the stability. I think you have also seen it. I talked about accuracy, but in stability, of course, we also win with a quality factor. So the larger the frequency, the smaller is this statistical noise, the scatter. And already like, yeah, more than 10 years ago, you have seen as soon as people switch from microwave clocks to optical clocks, you win orders of magnitude improvement in the Allen deviation. And I count on it, Fritz, that you introduced the Allen deviation, right? So this is the statistical measure of our stability. Fritz, is that correct? Hello. You slept. Okay, in the first row. This is courageous. You introduced the Allen deviation in your lectures, right? Thank you. Okay, now let's, after this short introduction to warm you up, let's start with the ingredients for the optical clock. What do we need? Well, how does an optical clock work? You need a pendulum. And our pendulum is the laser. The laser has a very high frequency, as said, so it's 10 to the 15, so 1000 terahertz. This is the optical domain. This is a very high ticking pendulum, but it's not very stable. So at first place, since the laser has intrinsic noise, we have to stabilize it to something like this. This is an ultra-stable cavity made out of ULE, and I will get into the details later. So this gives us the short-term stability. that enables us to do high precision spectroscopy and resolve very narrow line width. But then, of course, since this is a mechanical macroscopic object, it would drift away over time with temperature, pressure fluctuations, vibrations. So we need something else, and this is now the atomic reference. That gives us the long-term reference. So while the laser is driving quantum jumps between ground and excited state of an atomic transition, we're always interrogating the atom, whether the laser resonance is the same as the atomic resonance. And then we do a feedback loop onto the laser. And since we're here interrogating with atoms, that the transitions are only obeying the natural constants and the laws of physics, we can be sure now that our laser inherits the properties of the atom and stays constant over time. And now if I compare this frequency with my clock in Braunschweig in Germany, with the same atomic clock in Tokyo or in Pune, I can always be sure that the frequency is the same because I'm following the same kind of atom. That's the art of an optical clock. Now comes something technical, because now I have to measure the frequency here. 1000 terahertz is very hard to measure. There's no frequency counter that can do that. You can't do this electronically. And that's where the frequency combs come in. A very important invention of the last century almost, I would say. These are the frequency dividers. Both of these give rise to the Nobel Prize. So the frequency combs received the Nobel Prize in 2005, while the laser cooling and manipulation of ions was 1997 and 2012. So it's everything rather recent, giving this big boost to the optical clocks. And now in the following, I will discuss a little bit more the ingredients and tell you how to build a clock. Let's start first with the atomic system. So what types of atoms do you usually see at atomic clocks? I highlighted them in red here. So many of them are from the alkaline earth region. At the end of the lanthanides, terbium, lutetium, for instance, which is similar to alkaline earth atoms. Then you have something on the row of group 3, where you have actually, when you these are ions, so you rip off an electron and then you're left with a 2-electron system. Here you have forbidden intercombination lines, and here you typically drive, whether you have neutrals, you also have intercombination lines here because it's a 2-electron system. If you rip off an electron, so an ion clock, then you are doing quadrupole transitions. I will go into the details later, but that should just show an overview. These are selective elements. You can't use any of them because you first need good laser cooling transitions. Yeah, you have to manipulate and control the atom. And then you need a very good clock transition. And just looking at the periodic table where you have 1 or 2 electrons, valence electrons, not too complicated spectrum. This is typically the 2nd and the 3rd row, or the end of the lanthanides. Sorry, what? Gadolinium. I never heard about that actually. Who? This gallium. Maybe I wouldn't exclude that I'm overlooking a group in the world, but I'm not aware of the ticking clock here. So maybe there are experiments to start. I mean, of course, one can try and push, like SIN also has been proposed now recently, but people haven't realized it yet. Then people are also searching on thallium and thulium. So it's not completely exclusive. And in 10 years, maybe it will look a little bit different, but this is like operational clocks right now, yeah, that are really ticking. And yeah, maybe we can, it will be difficult, but yeah. So what I wanted to say in the next slide, I guess, is if you compare this now to quantum computers based on trapped ions, you actually see many of the same candidates. Well, what remains is here the aluminum, the alkaline earth row, and also terbium and the lanthanides, cadmium. So there's a very large overlap, and that's why when you're doing optical ion clocks, you're very close to the quantum information community. You have the same ion traps, you have the same ions, very often terbium and barium at the moment excelling, also calcium and strontium. So these are very, very similar candidates. And I will show you now when we're looking at the atomic structure, why. So what you have seen in Subhadeep's lecture was the hyperfine ground states that are used for microwave clocks. Yeah, you use the hyperfine splitting on the order of a few tenths of gigahertz. And then if you switch, so you can call this also hyperfine qubit if you make a quantum computer out of it. So a terbium quantum computer would run here on this hyperfine qubits. And they, of course, profit from the infinite long lifetime. But the same you can do now in the optical domain. So this is what we're doing with optical clocks, that we're going away from a microwave transition and exciting the atom to a high-lying electronic state. Ideally, it should be a very highly forbidden transition so that we have a long lifetime and get a very good energy resolution. So for instance, the S to D transition is very forbidden. It's a quadrupole transition. But at the same time, you can also make this as an optical qubit. People like Rainer Blatt and Innsbruck are doing this with calcium ions. So they're exciting here from the ground state to the excited state. This is now the pseudo spin of the atom is flipping from down to up. And since the lifetime is very long, on the order of 1 second, you can also store the quantum information there, and you can make an entanglement, and you can really profit from this long coherence times. So this is what I wanted to point out. If you're building a clock based on such an optical forbidden transition, it's exactly the same what people are doing who are encoding optical qubits in the systems. Yeah. Some people choose the hyperfine qubits, some people choose the optical qubits. And that's what brings us really close. Now the question is how you detect the qubit or how you detect the clock transition, because it's such a forbidden transition, such a forbidden quantum jump. This is the next question. So this is very forbidden. How do we detect it? We have here on the other side for very allowed E1 transitions. So this electronic dipole transition that you can use beautifully for laser cooling. You can scatter many photons. But if you excite the clock transition, how do you know whether it was down or up? Anybody an idea? Who has seen that already? The same trick you do with the optical quantum computer. And because here we hardly can wait for 1 second that the atom decays and sends out 1 photon. So you have 1 photon per second. That's ridiculous. But look at this beautiful transition. Here you have tens of millions of photons. Here we can scatter 10 to the 8 photons per second. Yeah? And that's why we do a trick, and that is called electron shelving. So once the qubit is excited to spin up, the population, the ground state is empty, and that means you can't fluoresce any photons here anymore. Yeah? You shelve, you park the electron here in a higher lying metastable state, and that means the fluorescence on the other transition, because it's such a V shape, just stops. But if the spin is down, if the electron is in the ground state, then you can scatter 10 to the 8 photons a second. So this is like a leverage, a magnification by 8 orders of magnitude. And I show you here a little video. I hope it works. Yeah. This is how you can optically detect the quantum jumps in a single trapped ion. So this is one of our terbium ions in our ion trap. And now we're exciting the quantum jump to the forbidden transition. We're parking the electron into the D state. And every time when this happens, the atom gets dark. When the atom is in the ground state, when the spin is down, it's bright. And like this, you can detect on this allowed laser cooling transition the quantum jumps on the forbidden transition. This is the electron shelving technique. And you really can watch by eye the quantum jumps nowadays of a single trapped atom. And that's really beautiful. You can image that on your camera. You can watch live how your laser is exciting the qubit transition. Okay, good. And this is just to summarize. So the forbidden transitions for the atomic spectroscopies here, it has to be something forbidden. It can be either quadrupole, octupoles is extremely forbidden, or intercombination lines if you have 2 electron systems where you have to flip the spin, anything that is deadly forbidden. Okay, now the clock laser. How do we excite the narrow transition? Since it's a very forbidden transition, the laser needs to have some pre-stabilization. So we better start out with a laser that has already sub-hertz line width, have a very good signal. How do we get that? Well, don't worry, you don't have to understand everything here. Just, I told you, I want to give a conceptual overview. And for those who are interested, if you want to build a clock, I put you here the references that are excellent references. These are the original ones. And Eric Black, that's a wonderful overview and introduction. It comes from the LIGO family. So how to stabilize lasers, how to make the best lasers in the world is of course a problem of gravitational wave detectors. So the people in the LIGO collaboration were among the first ones who thought about this issue. And that's why you have also Pound, Drever, Drever and Hall were basically working on that in the 1980s. And they found a trick that was from even earlier, from the 1940s, from how to stabilize microwave oscillators. That's why the technique is nowadays called Pound, Drever, Hall. So honoring all three men who contributed there. And this is basically the scheme how you can stabilize your laser. You need a high finesse Fabry-Perot cavity. And then this gives you a very high bandwidth lock. When you stabilize the laser there, you need a pocket cell or electro-optical modulator. You make the beat node of the reflected light with the incoming light, and then you beat it here. You mix it down to something that you can measure and make a servo back. So I will not go into the details, don't worry, because this would be many minutes or half an hour of lecture. But basically what I want to say here, so you have this high bandwidth lock, and when you make sure that the laser is following now your reference, the cavity, then of course everything in the end ends up at the cavity. How well can you isolate, and how good is the quality of your cavity? And that's why people make an enormous effort in the optical clock business to make the best cavities in the world. And it's rather remarkable because if you visit us at PTB, you will see actually the world record in the best cavity. That's the cryogenic silicon cavity at 124 Kelvin at the moment. And that gives us a stability of 4 × 10⁻17, so a laser in the millihertz regime. But if you don't want to go cryogenic, you can also build cavities at room temperature. For many applications, that's also good enough, especially for portable devices. You can imagine room temperature is superior. And this is how our room temperature cavities look like. And even here, we can get down to 1 × 10⁻16 in a second. So also really world record and quite remarkable. And what does it mean? So if you have a length of 10 centimeters or so, and you want to have a laser in a sub-hertz region, 10⁻15, that means that the length of the cavity must change less than 10⁻16 meter. So that's 1/10 of a proton radius. So can you imagine to build a macroscopic object that is not changing in over a few seconds to less than the diameter of a femtometer of a proton? And this is a huge effort that we have to make. So what you have to do, was one of my first PhD students in the lab, very proud of his first clock laser, and you see everything is super shielded. It's nicely packed in many, many, many layers. So thermally shielded, vibrational shielded, this is acoustic barifoam, and there you have everything packed in, again, insulators. You put everything on a vibration cancellation platform, active or passive. You low pass everything, you actively stabilize temperature to millikelvin. Passively, we control the temperature even to the nanokelvin regime. And this is, you do it by putting it like in like such an onion principle. So you have layer by layer by layer that is basically low passing temperature fluctuations. So you have copper shields and you have everything nicely gold coated, heat radiation. This is quite an art to build such clock lasers. And in the end, you're limited by something what we call thermal noise. So this is the Brownian motion of the substrate and the coating and the mirror and everything. Just by residual temperature fluctuations of a few atoms on top of the mirrors, you do get this Brownian noise. And that's a big issue. And actually a seminal paper, for those who are interested, I refer you to Numatha et al. 2004. That was really a breakthrough of people being able to understand the fundamental noise limit of these clock lasers. And that really pushed us in the community to understand what is now the recipe to improve it. Yeah? How can we reduce it? By increasing the length of the cavity, increasing the waste of our laser beam that we send into the cavity, reducing temperature, ultimately go cryogenic, and reduce phi, which is basically the instability of the material, the elasticity. So you need a very high quality factor. Let's put it like this. If you use a crystal which has a high stiffness, that gives you the best low noise. If you have a very soft material, you will also have a lot of thermal noise. So easy to say. So choose the right material and follow these parameters. And we have investigated that in our first paper in 2014, where we have published, in our case, all the different noise contributions. And you see there are many of them. The vibrations on the floor that we measure here at the level of 10 to minus 6 G is killing everything. That would be the vibrations if you just put something here on a good floor. So you have to put it on an active vibration platform. Then you have thermal noise. The thermal noise limit is a flicker floor, so it's very flat. Then you have intensity fluctuations, electronic noise, temperature fluctuations, the drift of the creep of the ULE cavity itself, how it's shrinking over time. So many, many things that you add up. And in the end, this is the signal of your laser that you get, and you're happy if you get close to the thermal noise limit. And what we saw is that our first cavity that we built actually for the terbium ion, we didn't have to do very fancy things. You see, it's just around a cylindrical cavity resting on this heat shield, which is out of copper and then nicely gold plated. And you just put it there. And you know that the vibration sensitivity of the bulk of the ULE material is 3 times 10 to minus 9 per G. So that's really enough to hit the thermal noise limit with such a cavity. But now if I want to go to an even better laser, because the longer the cavity, the better the laser. So the next one that we built for our indium clock is 30 centimeter long. And there actually the thermal noise level is already here at 10 to minus 16. And then we see we have to worry now about the vibrations because this sensitivity would be already too big. And now I tell you how you care about vibrations. Imagine such a long cavity. You can imagine the longer, the more sensitive to vibrations it is. And you can think of it like a banana. Yeah? You're shaking it and it's doing really this bending mode. So while the ground, the soil, everything is vibrating by seismic noise, your length of the cavity keeps changing because you're bending the mirrors. Yeah? And you have something which is called like the Poisson effect. When you squeeze something, then it gets longer. When you deflate something, it gets shorter. It's like an elasticity module. And these effects we can compensate actually. And this is what we did. We did finite element simulations. So what would be the best magic points to support such a cavity that the bending effect cancels the Poisson effect? And then by doing this, so this is the 0 line where your 0 sensitivity to vibration, we saw that if we put the mirrors off axis, so displace the mirror from the symmetry line, we can find such a sweet spot where we have 0 sensitivity. While when the mirrors are symmetrically mounted, as you initially would do it, then you never find such a crossing, never find a sweet spot. So that was finite element simulations. Now our PhD student had to do the hard measurements, opening and changing the cavity support, and we could verify our simulations with the measurements. And you could really see, lovely, it's if you build a perfect symmetric cavity, you never find a sweet spot. But if you displace the mirrors a little bit, you can cross and obtain close to 0 sensitivity. So that's very much needed. And then thanks to this suspension, our laser then reached the 1 times 10 to minus 16 thermal noise limit. And this is currently the optical cavity where we're operating the indium ion clock. Okay, now next ingredient. I was teaching first about the lasers. Now comes the frequency comb. Again, I have to apologize if I want to lecture about frequency combs. I need 1 hour, yeah, easily. So I just can give you again an overview. What is a frequency comb? Well, in a nutshell, it's a pulsed laser. and you just look at the pulsed laser in the time domain, and now you go to the Fourier domain, to the frequency domain, and you see every time when you have periodic pulses, that means you have a periodic spectrum in the Fourier frequency domain. This is why we call it a frequency comb, yeah? Because you have all these beautiful combs in the frequency domain. Now there's something else. You have the group and the phase velocity. So that means that when you have here these wave packages, the phase is constantly changing. From pulse to pulse, there's a delta phi and offset phase. And that means when you look now in the frequency domain, that the comb doesn't end up at 0, but there's something like a new SEO, a frequency offset. So when you extrapolate your comb to 0, you get this frequency offset. And that is directly proportional to this changing phase here. So if you have a pulsed laser, you do worry about two parameters, the frequency offset, FCO, and the repetition rate. This is you, the laser builder, deciding at what time do the pulses arrive, how often, what's the frequency rate. So T is 1 over F rep. So these are the two parameters, F rep and FCO, that go in. And now knowing these two parameters and stabilizing them, you can basically measure any frequency. And the way you do it is, well, schematically shown here. Well, this is your frequency comb stretching out over many, many frequencies. That's what the colors should indicate. And now you make a beat node measurement from one comb, and you look for something which is an octave away, so exactly half the frequency. You double it, and then you make the beat frequency. And like this, you can actually get rid of the CO. You can stabilize the CO frequency. Then the repetition rate, which is typically on the order of 100 of megahertz, you can lock to a maser or a cesium fountain or another ultra-stable laser. So anything that is stable, you can lock it again with a beat node, optical beat node. So if you have now stabilized F rep and FCO, so these two parameters are stable, the mode number, or I have to apologize, this N should be an M, N is M. So the mode number M can be measured with a wave meter. This is easy because the frequencies, these combs, they're so far away on the order of hundreds of megahertz that you can resolve it with a classical wave meter. So now I know M, F rep and FCO, and then I can deduce any absolute frequency. This is in a very quick hand waving nutshell how we use such a comb to measure any frequency Fn. And yes, of course. Because this is in the microwave, so it's not magnified. The CO has to be, everything that you do in the optical has to be at 10 to minus 15 or 18. This is completely correct. But if you, the repetition rate, this is totally sufficient if it's in the 10 to minus, yeah, let's say 14 or 15 rate like a maser is. Because it comes in, it's still multiplied by the M, you see. If you do the error propagation, the M is on the order of 10 to the 5. So this levers it to the optical, but the M is just a number. It doesn't have an error, it doesn't have a dither. So the dither is only here at the microwave frequency. So relative speaking, when you do error propagation, when you look here, okay, this is absolute frequency. Now let's look at the relative one. You divide it by nu, the 10 to the 15 hertz, right? So then you have some error that is dithering at the level of 10 to minus 5 or so, and you divide it by 10 to minus, oh, sorry, I said wrong. You divide everything by 10 to minus 15, which is the optical domain. But the dither in the microwave is also just so small. So it's practically the same thing, like delta. Exactly, yeah, yeah. Well, the dither in the microwave, the absolute dither is millihertz or so. But now you divide everything by 10 to minus 15. It's the same argument that I tried to give in the very beginning. And that's a really cool thing, since this number is known and it's absolutely fixed, you don't get any uncertainty. And the only uncertainty is this few millihertz from the maser. But the CO is a different issue. This you have to measure really to this high accuracy. Okay. Yeah, and what I also wanted to say, of course, you can use now the comb to compare directly via such beat measurements, optical to optical. Yeah, if you have a laser here at the orange comb and here one on a green comb, you can directly compare them by making beat measurements. And just that you have seen it once, if you have a simple pulsed laser, be it a Ti-Sapphire or a fiber laser, of course, it's not octave spanning, it's not so broad. So what people typically have to do, you send it through a nonlinear fiber where you have a very high intensity, then you get nonlinear cell phase modulation that broadens your spectrum. And after the fiber, the comb is really like a rainbow. Yeah, you can really get all the colors in. So these are nonlinear optical effects into this special fibers that you can get. And like this, you can stabilize the comb. And you can also then create the comb in different frequencies. You can even lock a red laser onto an infrared comb. So that's really cool. This is how it looks like, very messy. So nowadays you can of course get all commercial systems from companies, and you see this kind of combs in all the labs all over the world. This is then the electronic rack with all the counters and many BNC cables. So this is the typical AMO lab. And I think what's also very good to know, this is a very recent measurement from Eric Benkler at PTB 2019. He benchmarked the different combs and investigated what's the noise from the comb itself, from beat node to beat node. How much noise do you pick up in the optical? Because it's not so clear. And he did this beautiful measurement now in relative frequency stability over averaging time, how fast it averages down. And you see a free running comb would, for some things, not be good enough. But if you do end-to-end path stabilization, so really active frequency or fiber length stabilization, you can really go down to close to 10 to minus 22. So that's remarkable. So with this, Eric could show that at the moment, no optical clock worldwide could beat the comb performance. So when you build a clock, you might be limited by the clock laser or by the atom, but fortunately not by the comb. Combs are really on the safe side. But you have to worry. You can't just blindly put a comb. You really have to stabilize every element very carefully. Okay, now types of clocks. How much time is left? Is this counting down? Yeah, okay. Okay, types of clocks. What do we have? I categorized it now. This is my perception. We have on one side the optical lattice clocks with neutral atoms. On the other side, we have the ion traps, and with a single ion trapped in such classical Paul traps. And then very new generation is the multi-ion clocks and quantum logic clocks. That for this you need more complicated RF traps, and there we actually use the similar or identical ion traps that people are using for the quantum computer. There in this business we have a lot of synergies and overlap with the quantum information. So this is how I would characterize it at the moment. When I look at the world, what kind of optical clocks do we see? And I mean, the big competitors are, of course, the lattice clocks with the neutrals compared to the ion clocks. So in terms of the standard ones, not multi-ion, I would say neutrals profit, of course, from the high signal to noise they get because they trap many, many atoms, up to 10 to the 4, 10 to the 5 atoms. They have, for this reason, very short server times and high stability. On the backside, they suffer more from the collisions. They have higher order effects in the lattices, polarization dependence in the lattice. So they had to struggle a bit more in terms of the systematics. While on the other side, you have the ion clocks. They have a very good systematics. They have less problems than neutrals. but they suffer a lot from the short-term stability because typically they trap a single ion. And actually, no matter where you look worldwide, even in a quantum logic clock, only a single ion is used for the clock spectroscopy. And that's, of course, a really poor signal-to-noise ratio. So I would say that good accuracy and compact, while the others profit from the very good stability. But of course, it's a head-to-head race also in terms of accuracy. So just a glimpse, an overview of the lattice clock principle, and I will not go in details because we have 2 lectures on trapping and cooling of atoms. So I think you're familiar with the concept of dipole traps. You can throw atoms into a standing laser wave, and you can trap them in the minimum of the potential here. So it's typically the intensity of the light field. And then the big question was, well, if I trap an atom at the intensity of the light field in such an optical tweezer, in such a dipole trap, why don't I have huge problems with the systematics? Because I have huge shifts. And then an ingenious idea came up by Hidetoshi Katori in 2003. He published the ultra-stable clock with neutral atoms in an engineered light shift trap. And what he meant by this, he was searching for a magic wavelength. And this is typically where you have such crossings. This was an old calculation from my PhD thesis in magnesium. So these are the Stark shifts of the eigenenergies of the atom. And this is the ground state, and the blue ones are the excited state. And every time when the Stark shift of the ground state crosses the one of the excited state, so in such a crossing here, you have the identical Stark shift. So you see the atom cannot distinguish whether it's in the ground or in the excited state. The Stark shift is identical. And this is what we call the magic wavelength. And this is what you need to make a clock, to build a clock, because now if you drive the clock transition here from minimum to minimum, we don't get a shift in the difference of the energy. We still have the proper eigenfrequency of the atom. And that was this ingenious idea of Katori, that he proposed that, and that gave a real boost to the neutral atoms. You could locate them in the Lambda regime, you could do high precision spectroscopy without Doppler effects, and nevertheless don't have any Stark shift issues. And these type of clocks today have actually the world record in the most stable frequency standards. So with 5 × 10⁻17 in a second, that was published by Bothwell in 2019. That gives them a huge profit. But I should also say, and typically they have 10⁻³ or 10⁻⁴ atoms in the lattice. I mean, you might start out with 10⁵ atoms, but then you have to really cool it into the dipole trap. The dipole trap is rather shallow, so you need microkelvin temperatures. You lose a factor of 100 in the atoms. But nevertheless, this is a wonderful signal to noise, and that gives them the highest sensitivity and stability. On the other side, we have the ion clocks. And I already told you, here we're typically talking to a single ion only, one atom. Ion traps, I will not explain in detail. Martina and many other people talk about ion traps here. It's basically a shaking potential as indicated here. You see it's just a classical electrode. But since Maxwell tells you that the divergence of the electric field is 0, so every field line that comes in also has to come out, that means you always have such a saddle potential. It's confining in one direction, but repulsive in the other direction. And only when you apply a RF voltage so that you constantly change from plus minus, then you can confine the atom and you get this ponderomotive time-averaged shaking potential. And the special thing is that actually these kind of potentials, they're remarkably deep. We're not talking about micro millikelvin, it's 10,000 of Kelvin. So they're very deep. Even if you have a background collision, the ion remains and stays. The lifetime can be almost infinite. So in our case, the terbium ion has a lifetime of many months. You can keep an ion for half a year and talk to it. You can give it a name. So a PhD student sometimes only had 3 ions in his PhD life. And this is really very special for the ion traps. You also get the best coherence times. Also for quantum computers, the trapped ions have the world record in coherence time. You can shield this single atom perfectly from the outer world. You can cool it to the quantum mechanical ground state where the wave function is only 10 nanometers. So you know exactly at these 10 nanometers, what is the magnetic field, the electric stray fields, you can characterize the quantum system extremely well. And that's why also these ion traps have, or these trapped ions at the moment still have the world record in accuracy. So the best frequency standard is at 9.4 × 10⁻⁹. That's the aluminum clock at NIST, because you can manipulate this ion so well. And needless to say, since it's almost physically, mechanically trapped by such an ion trap, you can make it very compact and robust. So these are also very good candidates for very compact portable clocks. And the one who developed these techniques was, I mean, among others, of course, but Dave was outstanding and received the Nobel Prize for this, Dave Wineland, for the groundbreaking methods that allow to manipulate and measure the single quantum system, to really cool it into this very deep trap to the quantum mechanical ground state, to drive also with the laser the Fock states. These are the motions in a quantized harmonic oscillator. And these techniques are needed for the clock business, but also for the quantum computer. With this type of James Cummings physics, you can also build quantum gates and put everything in superpositions and so. Well, but the big problem remains for the ion clocks. I told you, you have a single ion. And now if you look at our stability performance, it's rather poor. In 1 second, we resolve something like 10⁻⁵ in frequency. And then the Allen deviation tells us we have to average with a factor square root of tau, and we have to average and average and average. And yeah, in something like 10 days or even 100 days, you only then hit the 10⁻⁸. And that's really a fundamental issue because we're limited by the quantum projection noise. This is as good as it can get, no matter what we do. Yeah, and waiting for tens of days is of course a big issue, a challenge for the lasers, a challenge for the signals that you can resolve. So this is a fundamental issue, how we can improve that. And needless to say, we cannot even dream about the Heisenberg limit if you have only one ion. So there's no need for entanglement. So this is how the multi-ion approach came in. And we proposed that more than 10 years ago in this paper. And coming from the neutral community, I was asking myself, why is it not possible to scale up the single quantum system to a many-body quantum system, as you wanted in a quantum computer with many qubits, to keep up the accuracy, to keep up the control. Basically, the challenge I put out is we need now experimental methods that allow us to manipulate and measure the many-body quantum system. A single ion quantum system is not good enough anymore for metrology. We need quantum metrology with many ions. And there we use the synergies with quantum information and simulation. And if we can do this one day, then we can not only classically lower the instability of the ions by going with a square root of n. One day we can also dream of entangled clocks, maybe reaching the Heisenberg limit, 1/n limit. We have less stringent requirements for clock laser, and we can also use it for the basis for the multi-ensemble clock, which has a 1/tau scaling. And I show you what I mean with the multi-ensemble clock. In our ion traps that are scalable and where you can have not only many ions in an ion trap, but you can also have like a linear or two-dimensional array of ions. You have many clocks inside one experiment. You have many ensembles, many clocks in one trap. And that's lovely because like this, I can also scale it up to thousands of ions. And I can do something which I call a cascaded clock. And of course, others also call it like that. So there are theory proposals and clever theorists calculating what are the optimal locking parameters. So I tell you how it works. If you have a clock 1 and you interrogate it with the time tau1, then you can use it as a flywheel. You can measure the phase of your laser and feedback on the laser. So you know the noise. Now you take the next clock, clock number 2, and you interrogate it with tau2, which is larger than tau1. I forgot the larger, sorry. So tau2 is larger than tau1. And then you go on. Then you go to a tau3 and tau4, and you cascade it like this. And every clock 1, 2, and 3 always gives you the information of the phase of the laser, and you can feed back on the laser. And then you measure with 1/tau, very quickly you average away the laser noise, and you can ultimately extend the interrogation time. And that's very powerful because then you have a 1/tau scaling and not 1/√tau. Because if you measure the phase of a laser, it's a phase measurement and not a frequency measurement. If you look into the Allen deviation business, then you see it's 1/tau. So this cascaded clock operation is very powerful to extend the coherence time to up to seconds. And this type of ion traps you can do in one tiny experiment and even make it portable. Yes, please. Depends what large means. I mean, with the octopole, it doesn't matter because the quadrupole shift is small. So a terbium octopole would be no problem. A terbium quadrupole transition, I mean, is limited by its lifetime anyway, then the cascadation doesn't make sense because you can't push it to long interrogation times. You really need an ion with a long lifetime. If you're looking at other things, lutetium or so, I mean, in principle, you can cancel the quadrupole shift in any ion by going to a magic angle, right? If you put your magnetic quantization field and with respect to the gradient, which is typically along the ion trap axis, then you find a magic angle, I think it's 56 degrees or so, yeah? And there it vanishes completely. So there you have 0 quadrupole shift. Then you only have to worry about the stability of the B field, how well you control it. The actual field gradients are actually very stable. We measured them and they're stable at 10⁻⁵ level. So this is fantastic. Even if you have a 100 Hertz shift, it's stable at 10 millihertz or less. So yes, I would say you can. And yeah, this proposal that we made a long time ago in 2012, that was made for our multi-ion ytterbium and indium clock. And then, of course, you need to make proof of concepts that it could work. But now we're very happy to see that more and more people are following up. So in the community in Singapore, there's the multi-ion lutetium proposal and clock, then the calcium multi-ion clock. The NIST has also published scalable protocols for the aluminum quantum logic clock. Then Dave Leibrand and Mariana Savronova proposed now multi-ion tin-2 clock, and Niels Huntemann at PTB is also working now with the multi-ion strontium clock. So this is catching up speed, and people see the big gain of putting more and more qubits into an ion trap to improve the signal and to more interesting protocols. Because otherwise it's really a fundamental limit, no workaround. But the high price that we had to pay, of course, is a lot of engineering and technology development. Yeah, so the classical ion traps would never work for it. So we built this scalable ion traps ourselves in our PTB clean room, and you see many scalable segments where you can operate many clocks next to each other. I will not go into technical engineering, but many PhD theses were consumed here. It has to be non-magnetic, ultra vacuum proof, temperature needs to be controlled. But it's very similar to a quantum processor. And actually now we're also engaging in building quantum processors for the quantum computer people in Germany. We're integrating also nanophotonics, waveguides to have really high scalability. I mean, we're doing this for the quantum computer, but for us, we do it for a clock on a chip. We really dream ultimately of the very compact multi-ion, multi-ensemble clock with thousands of qubits, where everything is on board, where you have the laser sources, nanophotonics, everything on a chip, just put on with a fiber array. So this is how it should look like. Fibers are coming in. Here you have breakout couplers. So we're doing the first proof of concepts and engineering these devices with the big fabs in Germany. But this is for the future, and there's a lot of fundamental research, of course, needed. Now I want to show you a video to see a little bit real-time experience from the lab, how it looks, how to load ions, because the lovely thing is you can see the single atoms by eye. And yeah, you see here, this is a loading process, and you see in real time how ions are loaded in such an ion trap. You can count 1, 2, 3, 4, 5 ions. You can also stop the laser if you have enough ions. And here I put the video where we don't have the repumper on. So you see actually when the ions are doing the quantum jumps, that makes it distinguishable. You see bright and dark ions. You see how they're hopping around during the loading process. The oven is still on, so we keep loading. And due to collisions, they're sometimes getting dark and bright. And this is really to give you an idea how slow it is. You can really have this in a very controlled way. You can say atom 1, 2, 3, and then if it's enough, after 20, 30 atoms, you just stop. But of course, you can load really a lot of ions. So you can go to 1, 2, and 3-dimensional systems. In the higher dimensional systems, you have typically temperatures below 20 millikelvin. In the 1-dimensional systems, you get even below 1 millikelvin. And if you go to the ground state, even 10 microkelvin. But here you have the highest control in terms of micromotion. Here you have to really worry more about micromotion because you have this spatially 3D objects. Skip here. But then how about, it's now a quantum many-body system. So we have now ions that are interacting. And basically you can think of many, many harmonic oscillators that are next to each other. Every ion has its own vibration frequency, but it's coupled. So as long as we couple them because of the Coulomb long-range interaction, now we don't have single vibrations anymore, but we have phonons. And that means if I excite an ion, I kick it, maybe with a laser pulse, I can be sure that all ions feel it and that I excite a phonon, a collective mode of motion. Yeah? And this is the important thing that is also needed in quantum metrology and in quantum information. We call this the phonon bus. So if you kick one qubit via this vibrational mode, via the phonon, you can be sure that the other ions, the other qubits feel what happened. This is how you can transmit the quantum information in the system. And this is a picture how these phonons look like. We can tickle them, we can stimulate and find the resonance. Yeah? So this is like the common mode of motion where all ions are oscillating in phase. Then you have the next higher order mode where you have out of phase mode. So if one node, the central ion doesn't move and the others are moving out of phase. The next higher mode, you have two nodes. So it's like the Egyptian mode. These go in this phase and the other there. And then you continue and continue. So if you have n ions, you have n modes, and you get always one node per phonon extra. I don't know how much time I have. Okay, so I just want to give you a very glimpse how quantum logic works in such a system where you use this phonon mode to talk to the ions and to entangle them, for instance. So quantum logic readout is very interesting if you work with ions that have inaccessible detection. That was also proposed by Dave Wineland a long time ago, and I think mainly by Dave Wineland. And the problem is that there are many, many species that don't have a beautiful cooling and detection transition, but maybe are good clock ions. So you have such a qubit that you want to excite, but you're asking yourself, is it excited or not? Is it in spin down? Is it in spin up? How can I read it out if the atom doesn't provide me by nature any good detection transition? Then the trick is we use a second particle. So either calcium, aluminium, or beryllium, and a highly charged ion, or a molecule. You always need a sparing partner, something that you use for sympathetic cooling. And then now we read it out via particle 2. Particle 2 is not a good clock ion and not a good quantum computer ion, but it has detection transitions. So what we do now, everything is prepared in the ground state. Particle 1 and particle 2 are in the ground state of the harmonic oscillator. That means the wave function is very trivial. So this is the quantum mechanical ground state, n equals 0. Particle 1 is in a superposition of being C1 and spin down and an amplitude C2 and spin up, while particle 2 is just in the ground state. This we know, we prepared it. So this is the starting point. And now we want to read out the quantum information of particle 1 via particle 2. So what we have to do is we do now sideband pulses. We shine in a pipe pulse, a laser pulse with a pi time to make a complete spin flip. So pi pulse means I have 100% excitation probability. But the laser pulse must have an energy which is resonant with the transition frequency, HF1, minus h omega 1. And omega 1 is the distance here of the phonons, this Fock states here, you see? So it's basically a red sideband pulse, which is decreased in energy, and it's just not enough to excite it. You see, you can't excite it. It doesn't hit the resonance here because it's decreased by 1 phonon. So that means if the atom is in a ground state, you cannot actually excite it. Nothing happens. But if the ion has been in an excited state, then something happens, because you see here, you find a resonance. You can actually, with this type of pulse, you can de-excite the ion, but it will end up in a higher order Fock state. This is the ground state, and this is n equal 1. So a red sideband pulse has the magic that it doesn't excite the ground state, but it de-excites the excited state, and it adds a quantum of motion. And this is the trick you do, because since now you put in a quantum of motion, you kick it, you can be sure the other particle will feel it, thanks to the Coulomb interaction, the phonon bus. Yeah, they're charged particles. One starts to oscillate, the other one will also oscillate. Now, if you look at our quantum mechanical wave function, we have seen now we have a superposition also in the Fock states, because if particle 1 was in the ground state, nothing happened. The whole quantum system stayed as it is, because there was no excitation. But if particle 1 was in the excited state, it got de-excited. It turned into the ground state, but it added a quantum of motion, a Fock state n equal 1. And this is now common to the whole quantum system because of this long-range interaction. So this is what the red sideband pulse did. Now we have to read out via the second particle, and we do this again with the pi pulse, a red sideband pulse, exactly like before, but now in the second quantum system. So the energy is diminished by hf2 minus h omega 2. Again, the same trick. If the particle is in a ground state, nothing happens. But if the particle is here in the Fock state n equal 1, then you excite it. It's exactly the same trick you play. And then you see what happens with the wave function. If you excite it, then the final wave function is everything is again in n equals 0. Both systems are in n equals 0. And now you have transferred the quantum information from particle 1 to particle 2. You see the superposition is now in the particle 2 state. So it's C1 times G2 and C2 times E2. And this is the magic in quantum logic. It's actually very classical. There's no entanglement. It's just kicking the ions and playing the trick with the energy difference that is missing. But now you could just map the quantum information, which was first in the first quantum system, into the second quantum system. And this is a system that I can detect, the electron shelving technique again. So that was very quick to walk you through quantum logic. If there are questions, please feel free to ask. Yes?
Yeah, so you're basically transferring state from the first particle to second, right? So like in the chain, you can transfer. Mm-hmm. Have you found out what is the fidelity of this process?
The fidelity depends on many things. It depends how well you're in a ground state, or you're 100%, or maybe only 99%. So the initial state preparation has to be good. And then the laser must be also very good. The noise should be very much in a carrier, not in a sideband. That's why many people have to filter the laser, send them through a filter cavity, because you can imagine if you have noise swings exactly here at the sidebands, that will kill your fidelity. So there's no general answer to this. It highly depends on your system in the lab. How good is your laser? How good is your ion trap, the heating rate, and so. But otherwise, the fidelity for clock operation, it's much better than needed, because actually clocks are not so critical in fidelity than quantum computers. You have to imagine, for a quantum computer, they want to operate with 100,000s of qubits and have an algorithm with many 10,000s of qubit swaps and so. And then if the fidelity is only 99.95, it's not good enough, because it adds up 10,000 times. For a clock, it's no problem. If you have a fidelity of 99% or even 95%, in the end, it's a digital measurement. It's dark or bright. And this noise is always smaller than other detection and technical noise. That's why I would say, thank God, for clocks, the fidelity, we do have to care about the noise issues of the laser, especially the side wings. But we are very far away from the high demands for a quantum computer, especially in the optical, because this quantum algorithm with 10,000 swaps and then even a fidelity of 99.95 is not good. So this is really a show changer. That's why quantum computers, many of them actually moving now back to the microwave regime, because it's so difficult in the optical to get a pure local oscillator that doesn't have the tiniest noise here in the sidebands. It's not completely decided. There are big companies and there are billion-dollar rated that are driving optical qubits, but more and more people also now trying the microwave qubits for the better spectral purity. Okay, yes.
Hello. Yes, ma'am. So when you were discussing about that calcium ion optical qubit, so you mentioned about the lifetime. It's about in the order of seconds.
Mm-hmm.
So when we use the hyperfine level, the lifetime increases. So that is one of the advantages. So is there any other advantage other than the lifetime for using the hyperfine level?
I mean, you always have to compare the lifetime with the gate time. When you build a quantum computer, think of the superconducting qubits. The lifetime is terrible bad, but the gates can be manipulated at nanosecond scales. They have very fast gate operations. So it's always the ratio between gate operation and lifetime that matters. So 1 second is actually rather long, and if you have fast gates, like for instance Chris Monroe has, on the order of picoseconds, then it's not a problem. So then the lifetime wouldn't matter. I would say it's more the problem with the noise spectrum, because if you have engineered microwave gates, they're usually much less noisy on the order of the optical transitions. And yeah, here I would see really the biggest distinction, whether you drive a microwave qubit or an optical qubit. For an optical qubit, you always need a laser. And in the end, the laser will decide what fidelity you can reach. This is really the struggle of getting the 99.999% fidelity. The lifetime, I would say, can be tackled if you have enough laser power, if you have fast enough qubit manipulation. But of course, it's also challenging. Infinite lifetime is nice, but most of the time not needed, I would say.
So other than higher lifetime, the hyperfine qubit, is there no other advantage?
I mean that you can eventually also drive the qubit excitation with microwaves.
Okay.
And this is my argument of the spectral noise purity, that microwaves can be easier handled. And then if you have to do the spin flip with a microwave, that typically can give you a better fidelity. But again, there's a lot of research and it's a head-to-head race between the different communities. So let's see how the world looks in 10 years. But I think there are sound arguments why microwave can be manipulated in an easier way and controlled in an easier way than optical.
Okay.
Yes, another question.
I have a question from optical comb. So, ma'am, in optical comb, you are using that hydrogen measure. But if you see that hydrogen measures instability can be degraded over time. So, and also we have other more stable than the hydrogen measures. So why we are not using other and using hydrogen measure?
I think that's going along the direction that also Subhadeep asked. Why is the noise of a hydrogen maser good enough for the optical comb? And this is because the hydrogen maser is only needed for the repetition rate FREP. And this is in a microwave. There, the noise is not an issue because it's not the optical measurement. You divide it afterwards. Everything is, it's a fractional quantity that we measure. You divide it by the 10 to the 15 of the optical. And that's why the noise of the hydrogen maser drops out. It's really not significant for the measurement. However, I mean, it also depends what you want to do with the comb. I mean, hydrogen masers mainly come in if you want to do SI measurements. If I want to really know the absolute frequency of my standard, I have to measure against the cesium fountain nowadays anyway. However, if you want to measure optical to optical, then you also can lock your laser on an optical reference. You can also, there are many different ways of doing it, but you can in principle also use the frequency comb and lock one pin to an optical reference. So then you have a breathing comb and then lock somewhere else. So there are many varieties for you to play around. And as long as you don't want to do as long as you don't want to ask how many hertz is my frequency, because then I need a cesium fountain and microwave standards. If you do optical to optical, it's rather free. Then yes, you can also get rid of even a hydrogen laser.
Another one question. So, ma'am, for that to beat the quantum projection noise, we have built that optical lattice clock where we can load 10 to the power 4 number of atoms. So, ma'am, why scientists are thinking about that multi-ion type of clock?
Because of the accuracies. Because, for instance, the strontium lattice clock, they're suffering a lot from systematic uncertainties. The black body radiation shift is orders of magnitudes larger than for ions. This was the slide I had comparing neutrals to ions. Many neutral, I would say all neutral atom clocks have orders of magnitude larger black body radiation shift than an ion. With an ion clock, I can easily operate at room temperature. With a neutral lattice clock, I always have to go to cryogenic environment. So this is much more complicated. Then you have collisional problems. You have, you're in this very shallow lattices. That means you have high unharmonicities. It's not such a perfect harmonic oscillator like you have in an ion trap. It's more like bending away. So you have to much more care about the motional state. Is your temperature here or here? Because then you have already distortions. The spectrum gets, the sideband spectrum is very nonlinear. It's a very funny distorted shape. You really, I really have a high esteem of people working with the lattice clocks and pushing them to the 10 to minus 18 level, but it's very complicated in terms of systematics. And certainly at a certain point, there will be also a limit if you want to push to 10 to minus 19 and further. Then they have higher order effects. The magic wavelength is just the first order approximation. You have hyperpolarizability, you have M1 and E2 transitions, polarization effects. It's really complicated. It's not so easy as it sounds at first sight. And then a big other issue that lattice clocks have is the Dick effect, because the duty cycle is very poor. So you have to load from a hot ensemble, Semans lower, mod, second stage mod, load in a lattice. So you have a lot of preparation time, and that means the duty cycle is poor. And that means you have something like a aliasing effect, a Dick effect. So the noise in your laser is down converted and projected into the clock measurement. So they have much more higher problems with laser stability. All these things you don't have in an ion clock. You only have the problem that you're stuck with a single ion. And that's why I proposed the multi-ion approach, because then we could get the best from both worlds, you see. We could profit from high qualities of a large sample of atoms and the high qualities of the super good state preparation of the ion clocks.
Hi. So in your EDIPM clock, you have used in 30 centimeter cavity. So for the locking rate. So you're using some vertical configuration. So you have seen some bending in this cavity. So what happened if you use that in the, you use the horizontal configuration, right? So if you use in vertical configuration.
Oh, it's doing the same.
So what is the problem in the
direction?
Okay.
Yeah. So everything is, everything what you look, it's sometimes hard to imagine, but when we have such cavities, we're actually sensitive to the waves at the ocean, which is 300 kilometers away. You see this because these are nanometer amplitudes, so 10 to minus 7 G fluctuations on the ground. And if you have a body putting it like this, it also has an eigenmode tilting in that direction. It's the same problem. And then the Poisson effect is the same. So you always have to think about the clever engineering, how to suspend such a cavity, be it horizontal or vertical. There are different concepts, but this horizontal thing, I found it very elegant because you not even had to engineer the ULE cavity, but just think of where do I put my mirrors, where do I support it, and it's free of any vibrational noise.
Hi, in that loading video that you have shown,
In which
loading of ions one by
loading?
one.
Okay.
So, like, what is the frame rate that I mean? How fast are you loading ions?
Oh, that was actually a real-time video. What I showed, that was the actual time.
Okay.
The one here.
So, are you using an oven or ablation?
We have both options. So what I showed was oven loading, so a constant flux, and then depends, of course, how hot you make the oven, because then the ions would arrive in a faster time. But we intentionally slow it down because we really want to have like 1, 2, 3. We want to have the camera counting it with particle detection, give us feedback, and then the computer switches off the loading process. And like this, we have a very deterministic control to one ion exactly. And we can tell our computer, please load 20 ions, please load 30 ions. So we intentionally slow it down. That roughly takes 1 second per ion or so. But you're right, we can also do it with a laser. We also have an ablation laser where each pulse gives an ion, then you have to pulse, 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 and then they would also come. There are many varieties, and nothing is as easy as you say, because some people have huge problems with ablation loading, because if you have a high energy and even other particles coming out from the ablation target, then they need minutes to cool down these hot particles. So it depends very much on which laser you use, which species. For ytterbium and calcium, we have found nice low power lasers that can give you very deterministic loading. So that works very nicely. But there are many varieties, and you have to choose.
Are there any further questions? If not, then let's thank Tanja for a beautiful lecture.